Hello everyone and welcome to today's lecture, Rules of Inference. These are all sort of in some sense interconnected ideas, but what we want to do is start with defining what it means to have a rule of inference in mathematics and why a rule of inference is so important, and kind of explain how that idea is connected to the idea of proving something in mathematics, constructing and writing down a proof. And lastly, what we can then do is come up with different proof methods for proving things using these rules of inference, and actually discuss the logical foundations of what are called axiomatic systems, because any mathematical structure, any mathematical idea is in fact contained within some axiomatic system. That you have to, when you start off trying to prove something, trying to create some sort of mathematical idea, you have to be working within some sort of axiomatic system that's a consistent axiomatic system. So that's what we'll talk about by the end of lecture today. But I guess the first topic today is various rules of inference. The rules of inference. And the basic idea in rules of inference, or about rules of inference, is that what we essentially do to define a rule of inference is take what we've done and expand upon it to give a system of proving things, or a systematic basis for constructing a proof. So we'll write the following definition. We say that a rule of inference, well, not two U's, just one U. Rule of inference in propositional logic and this is also our basis here is propositional logic, because predicate logic is in some sense contained inside this. A predicated statement like for all x, p of x, itself is a proposition. It's one single proposition. So the idea is that statements like this are actually contained inside propositional logic, which is really, really kind of nice. And this is kind of the basis of any mathematics text or mathematics proof. We're going to have a bunch of statements like this. For all x, p of x, there exists in x, such that q of x, stuff like this. Is what we're going to see in a mathematics textbook. So any and all statement like this can be summed up as just individual propositions that then we can apply these propositional rules to, specifically these rules of inference. So we say that a rule of inference in propositional logic is a sequence of propositions and a conclusion, such that the following is true. The argument P1 and P2 and P3 and all the way up to Pn implies Q is a tautology. So I guess this means that we should probably define argument as well. So an argument in propositional logic is a sequence of propositions and a conclusion. So the main idea here is that we want to be able to effectively make arguments in propositional logic. So if I can say form arguments P1 or propositions P1, P2, all the way up to say Pn and then conclude something from these arguments, the implication P1, P2, and P3, and P4, all the way up to and Pn, implies Q may be true, it may be false, but what we say is that a rule of inference in propositional logic is if we have an argument, so a number of different propositions and a conclusion, and this implication is a tautology, then we call this a very special type of argument. It's exactly a rule of inference because it's something that's always true regardless of the input propositions. The rules of inference occur in they're described more in detail in chapter 1.6 in the book. So I recommend reading this chapter to kind of supplement this lecture. But I guess the main idea is that there's a big table of them on page 72 in my copy of the book. It's table 1 in rules of inference. And I guess the main idea here is that I'll go through a couple of these to kind of show exactly what I'm talking about. So perhaps the most basic rule of inference that's always used is called Modus Ponens. So that's what we'll start with, and we'll just do a couple of these to kind of understand them. But I guess all of the rules of inference are important to know and understand. These can be found in table 1 in the book. So table 1, and this is in chapter 1.6 in the book. So rules of inference. I'm not going to be going over every single one of these rules of inference, but a number of them are things that will show up very, very often in mathematics. So it isn't kind of important to understand each one of these in turn. But we'll start with the first example, the first one, which is called Modus Ponens. It's the Latin. So this is essentially the statement that if a statement P is true, so if a statement P is true, and the statement if P then Q is true. So if a statement P is true and the statement if P then Q is true, then we can conclude that Q is true. So we don't know yet that this is a tautology, but what we're going to show is that this is in fact a tautology. This is always going to be true no matter what P is, Q is. If P is true and Q is true, then Q is also true. So we'll first go through with our basic method of using the truth table to show this in a number of different ways, right? We can always go through in either of the two ways that we know now. So by now we know how to use a truth table. This is, I guess, the first method of proof that we'll use. Proof, or the proof 1 we'll call it. So we got P here. We want to do if P then Q. So P implies Q. Know that it's true. It's if P is true and Q is false, it's false. It's true. It's true. So then we have the statement P and if P then Q is the and of this column in this column, or this row in this row. So it becomes true. It's and true and false is false, 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 because we have true here and false. We have false here and true. We have false here and true right here. So this is only true in this first column because if P then Q is true here, and P is true here, so the and statement between this and this is also true. But lastly, we have to consider the final implication statement, the final argument. The argument for modus ponens is the argument P and if P then Q implies Q. So we have to do the statement P and if P then Q implies Q. And sure enough, here we have P and P implies Q is true, going to a true value. So the implication this to this is true. And for each one of these, because we're starting with a false value in our implication right here, this is a true implication from here to here, here to here, and from here to here, because we always have the implication is true. And so what that means is that this is true, and this is true. And what we've shown is that this statement right here, the modus ponens statement, is itself a tautology, and therefore it's a valid rule of inference. I can say that if a statement P is true and the implication, if P then Q is true, we can then conclude that Q is also true. Q must be true. So the idea is that all of the things in table number 1 can be verified using this method, can be verified using the truth table. And some of them are longer, a little bit longer than this, and more complicated, because some of the rules of inference involve 3 statements. But the point here is that it doesn't really matter. Even if we have 3 statements, we can go through and do this truth table to show that all of the rules of inference in table 1 are in fact valid rules of inference. It's a very, very cool thing. So this is, I promise you, a different proof method. This is proof method number 1, using the truth table. Proof method number 2 involves doing, using our propositional logic. So we can still just use propositional logic to kind of do this as well, which is really neat. So let's do this in the second way. So we'll do proof number 2. So this is, typically when we end a proof, we can do a number of different things. We can put a box at the end of it like this. Sometimes sometimes we put a box like this. Other times you can put a box with an X in it. It's like shaded in sometimes, maybe. You could also put what's called QED at the end of the proof, which means querat era demonstratum, or in Latin, it essentially means the proof is demonstrated. But there's a number of different ways of ending a proof. And for basic logic, one way of doing this is through a truth table. Another way of going through and doing it is through logical equivalences. So let's do that. What we're going to do is use the fact that if P then Q is logically equivalent to not P or Q. This is something we've been using and proved a lot so far. But it's one of the big logical equivalences that we have, which means the statement P and not P or Q. And this is the same thing as this statement right here. The statement P and if P then Q is the same thing as a statement P and not P or Q. And one of our big logical equivalences that we have is the distribution of the and. So this is the same thing. It's logically equivalent to P and not P, or P and Q. And the statement P and not P we've talked about before. P and not P is a contradiction. In some sense, it's a fundamental contradiction, and we'll come back to it a little bit later. But you should be able to do a quick truth table to verify to yourself that P and not P is a contradiction. I mean, I'll do it up here if you want to kind of see it out. If we do a truth table for the statement P and not P, there's only one input to that statement. It's P itself. So you look at the statement P and not P. You know that P, it could be true or false. And let's move this over just a little bit. So not P, if P can be true or false, then not P is false or true for each one of these input values. And then P and not P becomes false, and it becomes false. This and statement is false, and this and statement is false. So this is exactly why the statement P and not P is itself a contradiction. It's not. It's a self-contradictory statement, which is fine. We can have contradictions, but the point here now is that this right here is a contradiction. It's a false value. So what we have here is that this is logically equivalent to a contradiction, or F, with an OR statement connected to this P and Q. Now again, in the logical equivalences chapter, back in chapter 1.3, we have that if we take a contradiction and we do an OR statement with that contradiction, it's just logically equivalent to the statement itself. And so this contradiction OR statement with P and Q is that statement itself. So this is equivalent to P, the statement P and Q. And this is matched, by the way. We can see that up here, the statement P and if P then Q is the same thing as the and statement between these two statements. So really that's all this is logically equivalent to, which is really nice. And what this means then is that when we look at the modus ponens statement itself in its entirety, of the statement P and if P then Q implies Q, what we've shown up here is that this is logically equivalent to the statement if P and Q then Q, because this statement P and if P then Q is the same thing as P and Q. And again, we can use our logical equivalence for this implication. This is the same thing as not P and Q or Q, which is the same thing from De Morgan's law as not P or not Q or Q, and which is the same thing as the statement not P or not Q or not Q, which is the same thing as not P or, this is a tautology. So not this should be not, it's not a not Q, which is a normal Q right here. This right here is a tautology, therefore this is not P or a tautology T. And from the domination laws, this is also a logical equivalence from table 6 in chapter 1.3. Not P or T is equivalent to just a tautology T. So without using a truth table, we went through and just used all of our basic logical equivalences. And you could make a valid argument that the truth table method is slightly easier, it looks slightly easier, but the problem here is that this is only it's only easier because there's less input statements here. In general, in like a mathematics paper, there are hundreds, if not thousands, of propositions, input propositions. And what that means then is that if there are thousands of input propositions, input theorems and axioms and whatnot, then what ends up happening is that using the truth table is not easy. It's not straightforward. It's not as straightforward as writing down a truth table with like 4 input components. If you have thousands upon thousands of input components here, this becomes a huge problem. Just like with the problem of the Sudoku puzzle, where you have 729 input propositions. Well, the propositional satisfiability problem becomes a much more difficult problem in that case. So the idea is that very often using basic propositional logic, it may look a little bit longer, but we can use propositional logic to prove that something is a tautology without even having to worry about forming the truth table. So I recommend that you go through and do this procedure for everything in table 1 in chapter 1.6. rules of inference in chapter 1.6. So it's table 1 in chapter 1.6. It's a good exercise to go through and do. I'll do one more here in the notes right here, so that you have an example of how to do it in the notes. But the idea here is that you want to be familiar with everything in table 1.6, because it's very often used. These logical rules of inference are almost always what are used in proofs. You have to use these if you're going to prove something. So I'll do the what's called hypothetical syllogism. So this is the next example that I'll do. I'm not going to do every example in the table, but I do recommend that you go through and do every example in the table just on paper at home to prove to yourself that you know how to do this. That's a good exercise. So the next one we call hypothetical syllogism. And this basically is the following. It's the statement that if P implies Q and Q implies R, then we can conclude that P implies R. This rule of inference is used to chain together mathematical arguments in a sequence of proofs. This hypothetical syllogism is a tautology that is going to allow us to make a mathematical argument by chaining together a sequence of arguments, sequence of proofs. Because if I can prove, say, that P implies Q, and then I can prove that Q implies R, then I have that P implies R as well, which allows me to then say that I can then use Modus Ponens to say that if P, so I guess a combination. This hypothetical syllogism is by its own. This is what we'll show. But if we have this hypothetical syllogism, and I can say that, so if P is true and P implies Q is true and Q implies R is true, then we can conclude that R is true. And this is how it would be used in a proof, say, because for a proof I would assume I would assume that P implies Q, or try and prove that maybe, and then try and prove that Q implies R. So if I have this, and this, then we can conclude that R is true. It's a combination of hypothetical syllogism and Modus Ponens. But I guess the idea here is the following. So we can do this just like before in one of two methods. I'll do called proof number 1, the truth table method. This is in some sense the easier method for us right now, but even now it gets a little bit more difficult, and I'm not going to want to do this by hand. I could do it by hand if I wanted to, but it might take a little bit too long. I'm going to use our handy truth table generator that we use from Stanford. I gave the link in the last lecture. We use this as follows. We want to construct this hypothetical syllogism statement right here. So we want to do the following. We want to do if P, then Q. We're going to do an AND statement. So AND if Q, then R. And then we want to do implies the statement if P, then R. And sure enough, using our truth table, we can see very clearly that this is exactly what we would expect. We have here that that for all possible values of input statements P, Q, and R, this statement right here, the statement if P, then Q, and if Q, then R, implies if P, then R. This is a tautology. So because of that, and I'll just write right here that the truth table. So by the truth table, it is clear that we can call it, if you want to call it statement S, we can call it statement S. S is a tautology. And I'll leave this up here for one more second so you can see that this truth table, no matter what, for any possible value of input statements, this statement right here evaluates to true. So it's a tautology, and therefore it is a valid rule of inference. Any tautology that you have can be seen as a valid rule of inference. And really, the main proof methods in mathematics are based on these tautologies or on rules of inference, which is why they're so important, and it's such an important concept to understand and define. As to the second method that we have of going through and proving this, we always in mathematics want to come up with multiple different ways of proving stuff. The second method that we have for proving this has to be logical equivalences. So without using the truth table, we have to be able to do it both using the truth table and without using the truth table. And very often, students will latch on to the truth table, jump onto the truth table to use the truth table. But the real power in logic comes when you understand how to use and do logical manipulations without using a truth table, without falling back on the truth table. Now, you always can fall back on the truth table, but it doesn't mean you always should fall back on the truth table. Specifically because for more complicated combinations of ands, ors, and implications, the truth table, it becomes messy and hard to interpret, whereas it's always possible to logically go from one step to the next in logical equivalences. So that's what we're going to end up doing when we go through and do this. So let's do this for hypothetical syllogism, just like we did it for the modus ponens before, the last step. So we might need a little bit more space here, so I'll kind of stretch this down a little bit more. But so the statement that we have here is the statement if P then Q, then Q, not Q. If P then Q, and if Q then R. This is, if P then Q and if Q then R should be the same, so if this is true, then we should also have if P then R. So we want to be able to do this without a truth table, and therefore what we do is we want to do the following. We'll use our first big logical equivalence, which is that this implication right here, and I'll keep this box like I did before. So we box this to denote that we use a logical equivalence on this implication right here, which is that this, so if what's boxed right here, then this is the same thing as the negation of what's boxed. So not if P then Q and if Q then R, negation of that, or the statement if P then R. And what that allows us to do is now use De Morgan's law on this negation. So this is the same thing as not if P then Q, or not if Q then R. I'll keep this entire thing boxed like before. I used De Morgan's law to get up to here. We got to keep this or right here with if P then R. And right, the idea here is, you might want to remember now, is that from before we showed that not if P then Q, this is logically equivalent to not P or Q, which by we use not P or Q is the same thing as if P then Q, and we then also now can do, this is the same thing from De Morgan's law as not P and Q, and not Q. don't forget the not Q right here. Gotta apply De Morgan's law correctly to get that this is the same thing as P and not Q. So what that means is that this not P, if P then Q, is the same thing as the statement P and not Q. We have an or right here, and this not Q, not if Q then R, is the same thing as the statement Q and not R, using this relationship again. We have or, an or statement between this, and then we have here just we can change this if P then R to not P or R as well. So what we have now is this big, I guess you can think of this as three or statements, or three statements chained together through ors that we want to see if we can interpret and figure out. So we have the statement P and not Q, or the statement, so Q and not R, and then the statement, so or not P or R. And the idea here is that we want to be able to show that this is a tautology. The question is, how can we do that? Is there an easy way of doing this? So at first this looks kind of daunting, but the idea is that we can sort of rewrite this by doing the following. We have a number of ors here, and remember, in terms of just when we're dealing with one operation, the or operation, we have an or. I can rewrite this entire thing as not P or the statement P and not Q. I'll keep this as one statement right here, or in the statement Q and not R, or the statement R. So this is the same thing. Basically what I've done is I've taken this Q and not R, I've switched this order here of these two ors. We have Q and not R or R. And I can also switch the order of this or, bring it all the way over to this side right here and put it as not P or P and not Q. And what that does is it gives me the following power. I can then rewrite this as, just use my distributive law to distribute this as not P or P and not P or not Q. And then I can do a very similar procedure here. This is the same thing as Q or R and not R or R, which is logically equivalent to true and, so a tautology, not P or P is a tautology. It's not, so true or not P or not Q, or Q or R, and again another tautology right here. And from the table 6, the domination laws in table 6, we have true and any statement is the equivalent of that individual statement. So this is the same thing as just not P or not Q, or the statement, same thing here, this just becomes Q or R, which is just a chain of ors. It's all logical ors, which means that this is the same thing as, say, you can do any order of the ors first. It becomes not P or not Q or Q or R, which is the same thing as, this is a tautology, so not P or R or a tautology T, which itself is a tautology from our domination laws. Okay, so it's a little bit longer than before. Like I said, right, some of these computations and these manipulations can be long expressions. But what we've done is we haven't used a truth table here, and we went through and just used logical laws to prove our logical equivalences. To prove our logical rules of inference from chapter 1.6. So I'm not going to do this for every single one of these logical inferences in table 1, but I insist that it's important that you do that just to make sure that you understand exactly what a logical rule of inference is, and you understand the process of checking whether something is a logical rule of inference or not. So just like before, we can kind of also, even if we want to, extend this idea of logical inferences to quantified statements or for all statements in their exist statements, so predicated statements, which is a very important idea. So it's worth mentioning that. I'm not going to go into it in detail, but we have what's called a number of different properties related to that in table. So if you look at it's table 2 in chapter 1.6, we have 3 extensions of the rules of inference to predicated statements. So this is table 2 in chapter 1.6. We see that we can do what's called universal instantiation. So this is the first thing in the table is called, and that's the implication that the statement for all x p of x. So we have that the statement for all x p of x is the same thing as the statement. Right, it's so if this is true, then we have that. We could say that this is the same thing as saying, so if for all x p of x, then p of c is true for arbitrary values of c. This is like these two things in some sense are one and the same. So universal instantiation says that the statement for all xc of x can be instantiated. If p of c is true for arbitrary values of c, right? This is in some sense the same thing as what we have here, and this needs to be a bijection, but we do refer to each one of these implications as separate implications. So universal instantiation is the implication that the statement for all x p of x, if this is true, then p of c is true for arbitrary values of c, and vice versa. Or the reverse direction is called universal generalization. And this is the reverse statement. It's the statement that p of c. So if p of c for arbitrary values of c, so if p of c for arbitrary values of c, then the statement for all x p of x is true. And so really what we have is a bijection between these two statements. The combination of universal instantiation and universal generalization gives us a bijection between those two statements. And likewise, we have a similar result for the existential quantifier as well. We can have existential instantiation, which is the same thing as the statement that there exists x p of x. This is the same thing. So if this is true, then p of c is true for some, possibly more, values of c. I'll make this exact, not just some, but it's at least one, possibly more values of C. And just like before, we have existential generalization. Which is the statement that is the reverse implication. It's that if P of C, some predicate, so P of C is true for at least one, possibly more values of C. So if this statement is true, then we have the statement that there exists X such that P of X. And so the idea is that we have a bijection between the there exists statement and the instantiation of that statement for both cases, but you got to be careful on how you use this. But what you can do then is make a statement like a mathematical statement, and this is often used like what's called a universal modus tollens. For all of the things that we talked about before, you can talk about universal generalizations of those rules of inference from the table 1. Remember, you should know all of the things in table 1 and understand what they mean. But the idea is that we can go through and do a version, in this case, universal modus tollens, I'll use as my example. In which case we say we do, we have the statement, say for all x, if P of x, then Q of x, and the statement, we have this. We have for all x, if P of x, then Q of x, and we have the statement that Q is not true, so not Q of A for some element A, for some value A. So this is true, say, and this is true. Then universal modus tollens says that we have that this is the same thing as P of A is not true. The negation of P of A for some value A. So we can conclude that P of A is not true. The statement P of A is not true for some value A, if we have that Q of A is not true for some value A, and we have that for all x, P of x implies Q of x. Because what we do is we use the fact that P of x implies Q of x is the same thing, or it's logically equivalent to if we have that P of x, if P of x then Q of x, this is logically equivalent to the contrapositive, or not Q of x implies not P of x. So this is the logical equivalence that we're using here. We say that if we have that not Q of A, so Q of A is not true for some value A, and we have the statement for all x, if P of x then Q of x, then our universal modus tollens it allows us to go and use this fact and this fact to conclude that P of A is not true for some value A. So it's arguments like this that are very, very, very common in mathematics and almost always used in mathematics. And it's why these rules of inference are so important. But that will conclude the lecture today. Thank you very much for tuning in. I hope you had a great day.